recording. So the very last section that we need to go over here in this module is section 2.4, and I think we do 2.5. I said 2.4b. So 2.4 is a section that is looking at adding forces in space, and that's the very same thing as saying now we're just adding the z-axis, okay? Now, we're going to see a lot of similarities to what we did in the x and y-axis, but now we're going to be doing it a third time, if you would, for that z-axis. And then, because of the perspectives that we have to take, there's a couple more variables that we have to be aware of, okay? Now, I'm gonna zoom in here a little bit. So the first application here is you're going to notice that we have this illustration, and it's part A of figure 225. So right at the top here of page 52, you'll notice that now that we are, you'll see that this vector A, or I'm sorry, this vector F that ends at point A here, you can see that it's tipped away from the x-axis, okay, kind of in front of it. And you can see that it creates this angle phi with the x-axis. So it's kind of, rotated forward, okay? So what that means is if I would look straight on the x-axis or straight on down that x-axis, I would no longer see true angles, okay? Because I'm now rotated a little bit here. So what I want to do is I'll also notice that if I try to measure F flat on the x-axis or even on the y-axis, it's always going to be foreshortened. I'm never going to get what we would call a true length of that vector or a true magnitude of that vector. So this section kind of looks at how we deal with that, So as we look down here, you're going to notice that we have this angle phi and we have this angle theta y. Theta y is always going to be what we call the y angle to in this case, the vector or the resultant, okay? And you'll notice that it's coming from the y-axis. Now, this phi is actually, as we rotate that x out, this is not theta x. This is the rotation that we're rotating away from the x-axis, okay? This can be positive or this can be negative if we go back on the opposite side of the x-axis, okay? Now, as we look down here, you're going to notice that that same force can have an x and a y component, but it's no longer called an x component because it's not along the x-axis. It's actually coming out along, and it's called h this time. Okay, h. So we're dealing with more letters. All right. So now as we look down here, you're going to also notice that this h component is going to be kind of along that plane, what we would call the zx plane, and that is going to be the length of it. That's going to be its component, and it's going to be swung by that angle phi. Okay. Now, a couple equations that we're going to be interested in is the one right down here. Okay. So now as we look, you're going to notice that if we want to find the magnitude of that force, this one's actually one of the easier ones. This is going to be the magnitude of the force is going to be equal to the square root of fx squared plus fy squared, and then plus fx squared, because if we look up here in this bottom illustration down the row, here's our x component, z component, and our y component. And if we take, if you would, a modified Pythagorean's theorem of that, just adding in the square of the fz squared, now we're going to have the length of that vector. Okay, so the first equation I want you to put on your equation sheet is going to be exactly that one. So it's equation 218, and it's going to be the magnitude of the force in space, F is equal to the square root of fx squared plus fy squared plus fz squared. This is z right here. Okay, that's our first equation we're going to put down. Now, the next set of equations that we're going to see are going to be on the following page. And it's going to be equation 219, okay? And 219, and I'll kind of pull over page 53. It's using these examples right here, and it's using the trig that we already know. So with the standard placement of the angle, our fx component is going to be equal to f times cosine theta. Our fy is going to be equal to f, the resultant, times the cosine of theta y. And then our z component is going to be that magnitude of that force times cosine of theta z. So this is, if you would, equations. There's 3 equations for 219, and I put those right here. This is the scalar component of each one of, or each scalar component of the force. So the x, the y, and the z. And when I say scalar, it's really just the magnitude of it. Like how long would it actually be in reference to how long that resultant force is, or F. Okay. Now, what's going to come in handy a little bit later is rearranging this for theta x, theta y, and theta z. So all I did over here was do that rearrangement, and that's familiar to us too. That's the trig that we know. The cosine of theta x is going to be the x component over its resultant, or its hypotenuse. The y over that same hypotenuse, and then the z over that. But this is just a rearrangement between these two using those 3 equations by equation 219. Okay. So again, in this case, it's not that difficult. It's just adding that z-axis with those familiar cosine functions of the angles. Now, something that's unique about this book that I haven't seen in other books, okay? The previous book that I used wasn't this one, but I mean, how they do it is okay, all right? Now, down here in equation 220, you've already seen some of these, and I've kind of intentionally not mentioned them because I didn't get them at first. And then now I'm like, oh, okay, now I got to figure it out. All this is, they're putting an I, a J, and a K to identify that they're indicating that each one of those variables is a vector. Okay, so you very well could write this. Do I have this one written? You could write this, as you've seen, the vector expression as f with a vector sign over the top of it is going to be equal to fx with a vector, but not the I. And then fy with the vector over the top, but not the j. And fz with the k, and then so on. So it would be one or the other, but it's the way the book is calling out that that's a vector. Okay, instead of putting the little line above it or the little vector symbol above the variable, or by putting the greater than sign for the operation. This is how they're calling it out. So all this means is the I, J, K is that we're using vectors now to find the vector magnitude of that force. So when I have a vector, that means I have both magnitude, okay? So I'm not just worried about just the magnitude here anymore. This means that I'm interested in magnitude and direction for each one of those quantities. So if you're wondering what those I, J's, and K's are, it's just like, oh, that's looking at fx as a vector. That's looking at fy as a vector and z as a vector. That's it. That's the difference. It's not just magnitude, it's magnitude and direction. So we can't add them algebraically. Okay. All right. Now that's what they're showing down here. They call that the unit vector. And that's why I asked earlier in calculus, do you guys talk about the unit vector? You did in Calc 3. Okay. All right. So maybe it's not as uncommon as I have never seen it like this, but I mean, I get it. I understand what they're doing. And so all this is doing is taking basically each one of these is equal to 1, and they're showing you the version of it so that now when they put it in back of each one of those quantities, that becomes a vector. So instead of putting the line above or that little vector symbol or using the greater than sign by the operator, they're using I, J, and K instead. Okay, so that's the only difference. And I will be along that x-axis, J will be along the y-axis, and K would be along the z-axis. So they would go correspondingly to each one of those vectors. Okay. 54. So let's kind of use some of what we've got here so far, which isn't a whole lot, but we're going to look at concept application 2.4. And we want to do what they're doing here. They said they have a force of 500 newtons. And the angles that it forms are going to be 60, 45, and 120, respectively, with the X, the Y, and the Z. So that means my theta X is going to be 60 degrees. My theta Y is going to be the 45. And my theta Z is going to be the 120. They want us to find the components Fx, Fy, and Fz of that force and express it in terms of the unit vector. So then putting the I, the J, and the K, or I like doing just the little symbol above. Okay, so just showing that it's an actual vector instead. So let's work through this example together. I know it's here. I'm not just going to point to it. I think it's important to go through these and write them out. So we're going to start with, this is concept application 2.4. And if you want to put the page number, you can. Page 54. Okay. And we have our force is equal to 500 newtons. All right. So this is known. So F is equal to 500 newtons. And then as the problem stated, theta X is going to be equal to 60 degrees. Theta Y is equal to 45 degrees. And theta Z is equal to 120 degrees. So now we want to find the X, Y, and Z components. So if we go back to our equation sheet, we are simply going to use these equations right here. Our Fx is going to be equal to the F times the cosine of the corresponding angle, the theta X. Fy is going to be F times the cosine of the theta Y. And then the Z is going to be equal to the cosine of the theta Z times the F as well. So Fx is going to be equal to F times cosine theta X. So putting our values. So remember, we're always going to show our equations in variable form first, and then we're going to put the values down below with any units. So in this case, our force is 500 newtons times the cosine of 60 degrees. So my Fx should come out to be cosine of 60, I believe, is 0.5, right? That's going to be 250 newtons, but do it on your calculator just to be sure. Make sure that you get the same answer. Good. Fy then is going to be F times the cosine this time of theta Y, or 500 newtons times the cosine of 45 degrees. So our Fy should come out to be 353.6 newtons. Okay. And then go ahead and do your FC. All right, did you get negative 250 newtons? Okay, so that's kind of finding the components, knowing the angles, corresponding angles with the force itself. Okay, so now, sorry. Now, as we look down here, after that concept application 2.4, now we're going to start looking inside of our box. And we are going to be kind of expanding out those forces. So for instance, when we look at the force and we say, okay, F times this portion right here is going to be that X component, that Fx, okay? The next but this is the vector quantity, remember, because we're adding the vectors here. So this is the vector of the fx. This is the vector of the the fy. And then this one is going to be the vector of the the fz. Okay. And what they did was they expanded out the x, y, and the z into their cosine equivalents with their angles. And the only thing, again, that I, j, and k do is to just say, these are vectors. Okay. So instead of putting the symbol up on the top, so it's taking that force times each one of those components. Okay. All right. Now, the next portion here is looking at the vector along its line of action. So you'll notice that they have this lambda x, lambda y, and lambda z. And all that is when we have our force, that's just extending it along that x, y, or z axis along its line of action, like to infinity, if you would. So, so I'm just going to keep those there right now. We don't need those on our sheet. So we're okay without those. That's kind of like an intermittent step. Now, the relationship among the cosines. This is going to be another one that we're going to want to add to our sheet. We know that cosine squared times theta x plus cosine squared times theta y plus cosine squared times theta z is going to be equal to 1. Okay, so that's a 224. If you want to add that to your sheet, that's going to be another one that'll come up a little bit later. I'll give you a chance to put that on. And then we're going to move down to our next concept application. Okay. Oh, I'm so sorry. Yep, I'm going to put that back down because I realized you might not all have the book in front of you. I'll zoom into it so you can see it a little bit better as well. And then we already had these expanded out from earlier, so you don't need to worry about those because we did that rearrangement. So now adding again, here's another practice problem, concept application 2.5. Here we're going to have a force that has the components Fx equal to 20, Fy equal to negative 30, and Fz equal to 60. Determine the magnitude of the force and the angles theta x, theta y, and theta z it forms with the standard coordinate axis. Okay, so as we look here, to find the magnitude, now remember, these are vector quantities, so we can't just take 30 or 20 minus 30 plus 60. These are vectors, so we need to use, in this case, it's going to be our modified Pythagorean theorem. We're going to take the x squared plus the y squared plus the z squared, and then take the square root. So that's going to be our first step. So concept application 2.5. This is on page 55 if you want to add that. Our first step is we want to find the magnitude of the force knowing the components. So F is going to be equal to Fx squared plus Fy squared plus Fz squared, and we're going to take the square root of that entire sum. So now, using the values that we were given, it's going to be the square root of, we're going to take 20. I'm going to use the symbol because, again, the L starts to look like 1 sometimes, squared plus, now this is a negative 30 squared. Negative times a negative becomes a positive. You could put the negative in there under, in the parentheses to square it, but I usually put absolute value because it's going to become positive anyway. So 30 pounds squared plus 60 pounds squared. So now our F is going to be equal to, it's going to be the square root of 4,900. And so you're going to get 70 pounds. And remember, when we're underneath the radical, that's going to be pounds squared. When we take the square root, it becomes pounds. The units also get that square root applied to it. So now that's the magnitude of the actual force, okay? So if we kind of go back here, this is the magnitude that we just got. Like, how long is that force in space? And we use the X, Y, and the Z components to find its magnitude, how long it was, okay? Now, the next thing we need to do is we need to determine what its angles are to our coordinate system. So we want to find, in the last problem, we were given theta, X, Y, and Z. We need to find X, Y, and Z. So to do that, we are going to use that rearrangement that we just looked at. We're going to say cosine theta X, for instance, is going to be equal to, now that we know our magnitude of our force, we're going to take the Fx component of that force and then divide it by the total force that we just calculated. So our cosine theta X is going to be equal to Fx divided by F. Okay. And I know my Fx, it was given in our problem. I should have written it here. I usually like to do that, but it was given in our problem as 20 pounds divided by 70 pounds. Make sure you put your units in here, cancel them top to bottom. And then we're going to take 20 divided by 70, and we're simply going to do the second function tangent, and that's going to be 73.4 degrees, which is what the book has for theta X. Make sure you put the X there. Okay. Now we're going to do the same thing for theta Y. See, a lot of this is like, okay, we do it once. Now we got to do it 2 more times because we got 2 more axes. So now we're going to do that same format. Cosine theta Y is equal to Fy divided by our X. And we know the Fy from our problem was, now here we have to put the -30 in here. Okay, make sure you put the -30 over the 70 pounds. Okay. Pounds cancel, and our theta Y is going to come out to be 115.4 degrees. So a box around that. Make sure you can get that on your calculator. I'm going to make sure virtually we're doing okay. And then our last one, imagine how we do that one. This is going to be our cosine, cosine theta Z. It's going to be our FZ over our F, which is going to be, our Z was given as 60 pounds divided by the 70. So theta Z is going to be 0.85. Oops. Duh. And you have to do the cosine function, 31.0 degrees. There we go. So finding the magnitudes, the components, and then the angles, pretty familiar at this point so far. Okay. Get myself straightened out again. Where I'm at page wise. 56. Okay. All right. The next thing we're going to do is we're going to look at section 2.4b. Okay. And this is force defined by the magnitude of 2 points and its line of action. So just like in X and Y's, there are instances when we know where a point is in space and we want to know where it is in relationship to another point so that we can determine like what is the distance between those 2 points. It's kind of what we're doing here as well, but we've now got a z-axis. Okay. So you'll notice that we can find where, you know, the line of action of a force is if we know 2 points in space, X, Y, and Z for each one of those. Okay. So you'll notice along here that we have a distance, in this case, I'm gonna go back up here, of MN. And this is going like across the actual cube, if you would, okay? From one corner to another. And this is length of MN. That is a vector. Distance is a vector because we know, how long it is and we know what direction we're going in. So you'll notice here that MN is going to be equal to dx, that's distance x vector quantity, plus the distance y vector quantity, plus the distance z vector quantity, okay? Then what we can do is we can say, all right, if I know what the magnitude of that force is, or I can find the magnitude of that force, if I know what its line of action is, that's the lambda, but I can expand that out and I can say, all right, F over D times the distance in the X, the distance in the, plus the distance in the Y vector, plus the distance in the Z vector. And this will make more sense when we put some numbers to it, okay? So what you're gonna wanna do is, trying to think which one here. I don't think we did any one of it. It's these down here. These are going to be the ones in the blue, 229. We're going to copy down fx is equal to the vector quantity f times its dx value divided by the overall d, okay? And that's the total length of that line. And then do the same thing for the y and the same thing for the z. So this is equation 229. I'll kind of zoom in here a little bit. So in case you don't have your book in front of you. So we want to do the x, y, and the z versions of each one of these because that'll be the components of that vector along each one of those axes. And then, as we know, we're going to need the corresponding angles as well. So then equation 230, is going to be the cosine theta x is equal to, now using those distances to each one of those points, dx over d, dy over d, and dz over d. I don't know what it's called. It's just called right here. Oh, it says just the directions of the cosines for that force. So it's equation 230. Now, we can add these vectors in space as well. Okay, so we're gonna see some familiarness here too. So you'll notice that to get our resultant of a force, we would need to sum all those forces in space. But we know that each one of those vectors, if there's more than one, is going to have x, y, and z values. Okay, so as we look here, to get the resultant x, the resultant y, and the resultant z, now we need to sum the forces in each one of those directions respectively. So the resultant x component of a force in space is going to be summing all of those forces in the x direction. So when you have multiple forces, you need to look at each one of their x values. Okay. Then do the same thing in the y. The resultant y component is going to be summing up each one of the y components of each one of those forces in space, and then the z. So we stopped at x and y before. Now we're simply adding in the z. And now as we look in terms of resultant, once we have all of those resultant components, right, x, y, and z, now we're going to use those to determine the resultant magnitude. So it looks familiar. A resultant is going to be equal to the square root of the resultant x squared plus the resultant y squared plus the resultant z squared. Okay, so this is, first we have to add up. This is when we have multiple forces and we want to find the one force that will replace it. But now again, the additive of the z-axis here. And then correspondingly, to find the direction of that resultant, we need to use cosine theta x is equal to that x resultant component divided by the resultant itself. And then same format for the y, and then for the z. Yeah, good. Okay, cool. We've got all of our equations down, I think. I think there might be one more, but we'll add it when we come upon it. Okay, we've got two more practice problems to do that'll kind of bring these things together. I know it's hard sometimes to just like look at these, but let's get them down in our work, and then by doing these problems, I think it'll help bring it together. So does everybody have these two equations all set? Okay, all right. So now what we're going to do is we're going to do a problem that is going to kind of illustrate what we're looking at here. So let me get my notes in place here. This is going to be sample problem 2.7. And I just want to get my equation sheet out in my notes. Okay. And I'm going to start a fresh sheet here. Okay. So sample problem 2.7, this is on page 58 in your book. Okay. Let's zoom in here. We've got, it's a tower guy wire is anchored by means of a bolt at A. Okay, here's where it's located. The tension in the wire is 2,500 newtons. Okay. They want us to determine the components of that force. So Fx, Fy, and Fc, and angles X, Y, and Z. All right. Now, as we look here, it might not look that, that difficult, but the deal is there is a distance back, oopsie, there is a distance back where A is from what would be the standard X, Y, Z axis. So down the tower is where our 0, 0, 0 is right here. And you'll notice if we bring our X axis out, our A is 30 meters in back of it. Do you see that? It's not along the X axis. There's our Z. That's our, I shouldn't say it's a problem. That sounds negative. I don't know. 2 is easier than 3 to deal with. That's all. So I've got my Z axis there. That's the difference here. So now I can't look at it straight on in the Y X axis and measure it. It's actually, longer because that A is further away from me. Okay. And then if I look at it in this direction, same thing, because it's going up and at an angle, I still can't look at it straight on. So I have to go through the process or some of the equations that we just looked at. So the strategy that we're going to take here is we're going to look at these distances that we have along where the coordinates are. So we're going to find that we have a dx, a dy, and a dz. Okay, and these are all going to be measured from the 0, 0, 0. Okay, from the 0, 0, 0. Now, here's where looking at it in a couple different perspectives, looking down from the top, looking from the front, and then like a right side is going to be helpful to understand why something is positive and negative. Okay, so I'm going to take time to kind of draw this out looking straight down. So we're going to look at sample problem 2.7. And the first thing we're going to do is we're going to draw the diagram of looking straight down, front, and then a right side view. So I'm going to start looking in my top view here, down the Y axis. Okay, so my Y is going to be a point. My Z, my positive Z is going to go down in this direction. And my positive X is going to go off to the right. Okay, positive X. So that's our kind of our standard. So if you would, if I look here, my Y is going up the tower, my Z is coming forward, and my X is here. I'm looking straight down right there on that tower. Okay. So what that means is that my A is going to be over 40, but it's going to be back 30. So A is like right here. Okay, that's going to be point A. And its distance right here is going to be 30 meters back. And it is going to be 40 meters to the right. Okay. Now, you're going to notice, I'm going to actually put these values here. Dx is equal to a negative 40 meters. Dy is equal to 80 meters. And dz is equal to 30 meters. Okay. I'm also going to put up here my convention. Now, our standard convention, y is positive going up, x is positive going to the right. Now we have to add our z. Our z is going to be positive coming forward, okay? So in the orientation that we see here, this is our positive z. Does that make sense to everybody so far? Okay. Now, as we look at connecting, so the guide wire, when we connect it from the origin to our point A, it's going to be along this axis right here, right? And if we look at our illustration, we know that our F force is going from A to B, right? So this is also point B here, right? But it's looking down the y-axis. So that means that that force F is along right here. This is force F, right? That's force F along that guide wire. Now, let's look at components. If that's the case, if that's in that direction, if I pull this over and I go down with this, do you see how that, and I gotta move this. Do you see how, this is 30 meters. This is my FX component. It's going in a negative direction, right? That's why our distance is a negative value. Took me a while to get that because I'm like, why are they calling that negative? If it's going to the right, the 40 meters is to the right. That's a positive direction. No. It corresponds to the direction of the vector going down. So it's a negative 40 distance, okay? Because we're going to be using this as a vector, okay? It does make sense. Now we're going to be looking at the Z. I'm sorry, I did that wrong. There's my Z is going in a positive. Dang it. See, this is why I hate this. This is my F. Here is my FX. I'm so sorry. I just screwed that up. My FX is going negative. It's going to the left. My Z is going down, which is positive. I'm so sorry. But the left is negative. That's why the dx is negative, because my x vector is pointing to the left. Sorry. So z is going down in the z direction, and x is going to the left in the x direction. Dx is negative, dz is positive. Practice that before class too. I looked at that a couple times because I knew. Now let's look at our front view. Okay, so this is our positive z. So now we're going to look in this direction and draw this, okay? So we're going to look down the z-axis as a point. So I'm going to give myself a little bit of room. Here's going to be my z-axis right here, okay? That's going to be my z-axis. My y is going to go straight up like this, okay? My x is going to go over here. I'm going to kind of make it extended a little bit. And that means that I'm going to kind of try to put it in line here. My A is going to end up right there. Okay, and that's going to be A. And then up here is going to be B. So now we know that guide wire is on a line between A and B. We know that our force is along that pointing towards B, as given in our problem. So here's our force. So if I want to show my y component, it's going to go up Do you see that? In the y direction, this is Fy. My Fx is going to go to the left, which makes sense. Just like it did in that top view, this is Fx. But remember, I can't measure them as true size in either one of those views because it's either forward or back to me. Okay. So perspective, is it kind of making sense a little bit? Not yet. Yeah, it's okay. Go with me. But now we'll see that because Fy is positive, that's why the direction of dy is positive. It goes along with the direction of the vector. And now let's do our right side view. I'm going to make this a little bit shorter. Okay. Our right side view, we're going to now look down the x-axis. So our x-axis is going to be here. Our z positive is going to be to the left. Okay, this is z positive. This is going to be our x-axis, but it's also looking down our x-axis. Nope. So that's going to be our z there. Our y is going to go straight up, right? Our y. So that means b is going to be on here. And then as I look down that axis, I'm looking now in this direction. Our a is going to be 30 meters over here, right? This is going to be 30. Going to be along that. This is going to be our A. This is going to be our B. And then if we show our guy wire, we know that our F is going to be along that. Here's our F. So that means our Fy in this orientation. And then we're looking down the x-axis. So this is actually along the FZ axis going to the left. We see it in that orientation. Our X is going like into the page on A. And then this again is going to be 80. Oh, and I didn't do these dimensions. This is going to be 40. It's in orthographic projection. This is 80. So just to try to give you a little bit of perspective of where we're at, and because of it being offset, that A being offset from the x-axis, we can't use just the x and y components anymore. We have to put that z in there. Okay. All right. So now we want to find the length of line A to B. Okay. So A is here and it's going up to here. All right. So what we're going to do is we're going to use those distances. Okay. The 30, the 40, and the 60. Wait, I'm sorry, 80. The 30, 40, and the 80. So the length of line AB is going to be equal to, and this is a line, the square root of dx squared plus dy squared plus dz squared. Okay. And those values come from the coordinates from the 0, 0, 0 that we were given at the beginning of the problem. Okay. So the dx is going to be negative 40. If we're going to square it anyway, so whether you put 40 meters in there or negative 40, doesn't matter. We're going to square that value. Plus the dy, which is 80 meters squared, plus the dz, which is 30 meters squared. And that's the length of AB, the length of the guy wire. All right, the length of the guy wire. So our length of AB is going to be equal to 94.34 meters. Okay, it's going to be a number that we're going to use. So again, we can't get it from any one of these triangles. We see this A to B, A to B, A to B, but because it's offset from that X and Y axis, we can't use sine, cosine, or tangent by itself. Okay. All right. So we used our modified, if you would, Pythagorean theorem to get its length. So how long is that distance? Okay. Now, what we want to do is we want to use the vector expression of, I'm gonna write this out here. I forget which one this was equation-wise. Hold on, I'll find the equation. We're gonna use the F is equal to Fx plus Fy plus Fz. Now, in the book, they're gonna show this expression as I, J, K, all right? And these are the vector versions of, that's all that is. It's like finding the vector of. And that just means that we have both magnitude and direction, not just the scalar value, not just the length. We need the magnitude and direction, so we can't add those algebraically. Now, to do that, we are going to take our F. It's going to be equal to, F is going to be equal to F times, okay? And this value is going to be the AB divided by AB goes on the bottom. The top is going to be our F vector, okay? And we're going to multiply that by the negative, I'm going to put it in variable form first. Dx vector plus the dy vector plus the dz vector, okay? Now, putting our values in here, this is going to be the vector value of the F. Now, the F in our problem, it told us that the tension in the guy wire is 2,500 newtons along that line. So that's going to be our F on the top here. So 2,500 newtons divided by, and this is going to be our AB value of 94.34 meters, okay? And then we're going to multiply that by our negative 40 meters, okay? Plus vectorially our 80 meters plus 30 meters. Okay, so that's our I, J, and our K, or our X, Y, and our Z. Okay. Now, as we multiply across, divide by the bottom, you're simply going to cancel out the meters, and we're going to be left with our F vector. And our F vector is going to be equal to, we're going to take 25 over 94.34, and our X value is going to be 40, negative 40 times 2,500 divided by 94.34, and that's going to be equal to a negative 1060 newtons. Okay, and that's going to be our I, or the FX vector. Plus vectorially, we're going to do that same thing, 2,500 newtons over 94.34 meters multiplied by our 80 meters. So that's going to be 2120 newtons, and that's your J, or your FX vector. And then FY vector. And then our Z is going to be the 30 times the 2,500 divided by the 94.34. And that number is going to be 795 newtons. And that would be the K, or also the FZ vector. Yes.
Is it okay to like split it up and like find the FFX, find the FY, find the FZ?
Yeah.
And then add the vector units instead of doing it all like.
Oh, yeah, you know what? Yes, that's okay. If you feel that that makes more, yeah. You can separate that out if you wanted to. So I know what you're saying. Yeah, that's totally fine. Mhm. So now what we've gotten is we have the components, the X, Y, and the Z components of our overall vector. This is that 2,500 newtons here. Vectorially, adding these three together is going to get us our number. How would we check that to see if we got that right? Could we check it? What would you do?
Add them together.
Careful.
See if they match.
Okay, so add these algebraically. Okay, try it. Let's go. Let's see. Let's see if they come out. You would do the modified Pythagorean's theorem, exactly. So to do that, and this is a nice check, what we should get is, we know that the magnitude of our F is equal to 2,500 newtons, right? This should equal the square root of, what is it, 1060 squared plus, and I should put my newtons in there. I tell you, you guys got to do it, so I'm going to do it. 2120 newtons squared plus 795 newtons squared. Let's see if that comes out to 2,500. Shoots, I did it. Yes. I get 2,500.005 zeros and that kind of thing. Yes. So you kind of see what we did there with that ish? No, that's part of our final answer, right? We got the components. So we can say that our Fx is equal to a negative 1060 newtons. Okay, that means that it's pointing towards the left, the negative direction of the X. The Fy component is 2120 newtons. It's positive, so that means that it's going up, which we saw on all of our diagrams. And then our Fz is equal to 795, kind of coming like that forward direction, right? Towards us in the positive direction. So these are the components of that guy wire. Okay, those are the X, Y, and the Z components. The second part of this problem is finding the angles to the X, Y, and the Z. This is the easy part. So if you remember on the very first page, we rearrange those equations. So if we take cosine theta x, it's going to be equal to the fx over the f. Or in our case, yeah, fx over the x. We use those same variables. The theta y is going to be the fy over the f. And the theta z is going to be the fz over the f. Okay. So you can say cosine theta x is going to be equal to our fx over our f. So we know that our fx is, put the negative in there, negative 1060 newtons divided by 2,500 newtons. Newtons cancel. Make sure you put your units in there. So our theta x is 115.09 degrees. Okay. Then we're going to do the same thing for the y. Cosine theta y, fy over fx. And our Fy is 2120 newtons over 2,500 newtons. Newtons cancel. Our theta y, 32 degrees. And then lastly, our cosine theta z is going to be equal to our Fz over our f. So our z is 795 newtons over 2,500 newtons. Oh, yes, Lex.
On the equation sheet, how do you know when to use, like, for solving for the angle, when to use the forces or when to use the distance?
It doesn't matter. You'll get the same value either way, because remember, those distances are along the length of the forces. So just because I had the forces handy here, I could very well use the distances as well. I'll get those very same values because it's along the same lines.
Okay.
Yeah, either way, either way. So our theta z is going to be 71.5 degrees. Now, I didn't plug this in each time just because I did mine on I have my notes here that I worked this all through. Make sure on your calculator, you're getting these very same answers. I trust that you're kind of at least checking as we go along, because once you do it once, it's the same thing 2 more times, right? Yeah. And then, so then this goes over and then, yep, our angles all correspond. Questions? All right. Now this problem, we look at our thing. If we look at 56, problem number 56 on our homework, I believe that that's going to go along, because you'll notice here that the answers that I'm giving you the f, x, fy, fz, and then the theta x, theta y, and theta z. Okay, and that's going to be a kind of similar process to what we did for that last problem. Trying to find. So 56, let's that one. So if we look at, I'm going to go back underneath here. So the problem that we're looking at. Okay, so problem 256 is the problem that you're going to be looking at here. And it says determine the X, Y, and Z components of just the 500 Newton force. So just this one over on the right, okay? One force, not of the two, just of the one. And this is going to be similar to what we just did right now, where we had the guy wire was really what that force is, that 500 Newtons. We were given 2,500. And then now you have your, your distances from the X, Y, and the Z. So you're going to want to find then the theta X, the theta Y, and the theta Z, and also the X, Y, and Z components using the information there. Okay. Now, in this case, we're given angles as opposed to distances. So it's very similar, actually. All right. So that's the first problem that you have to do that relates to this. The second problem that you're going to have to do is going to relate to the second sample problem that we're going to be looking at next. This is going to be sample problem 2.8. 2.8. So this is our last practice problem that we're going to be doing. Looking at our time here. Why don't we take, I got to kind of organize my papers here because I've got things in 8 different directions. Let me, give me 10 minutes. We'll take one more short break this evening, and then we'll come back. I'll kind of straighten my stuff out here and we'll do this last sample problem, and then we'll have what we need to finish up the homework for module 2. So I am going to